This is the solution to problem 466 of Halliday, Resnick, and Walker. Let's go over and look at the problem here. Somewhat of an unusual problem, I would say, that doesn't directly relate to any particular formula. It really forces us to sort of think carefully about circular motion. So what do we know? We're told that the particle is moving along a circular path. It's sort of on the xy plane and constant speed, so that means it's a uniform circular motion. And then we're told at this one time here, at this particular instant, where the object is and what its speed is. And then we're given some more information sometime later at t is equal to 10 seconds. So let's do a little bit of work here and see if we can make some sense out of this stuff. So let's draw a coordinate system first. That's always the first thing to do, of course. And then we're told at 4 seconds, it's at the point 5 meters, 6 meters. So we can sort of put the particle in there at that particular point. And then the problem says that it's got a velocity of 3 meters per second in the positive y direction. So let's go ahead and draw that. And then this next piece of information says the acceleration is in the positive x direction. So we can draw that acceleration in there. Now, what does that all tell us? Well, we know that the centripetal, that an object going around in a circle has acceleration. We call it centripetal acceleration. And that centripetal acceleration is pointed in towards the center of the circle. So that means we can pretty much write down or draw what the motion, the path is going to be. It's some sort of a circle there, as shown in red. The particle is right at t is equal to 4 seconds, headed directly upwards, but it's going to circle around and come back to the original point at some point. Now, the problem is, of course, we don't really know what the radius of this circle is. I drew it there, but we could make it sort of any size we want, and everything could still be consistent. We still got the velocity tangent to the curve at that point, and the acceleration pointed into the center. So what do we know? Actually, no matter what radius we have for this circle, we can determine something. I think we've got the other point here at 10 seconds. It says velocity is 3 meters per second in the negative x direction. So that's consistent anyway with our sort of picture. And it says the acceleration's in the positive y direction, so that's good. The acceleration then is pointing up this way. So that's all consistent. But we don't know where this point is. We're not given that information. All we know is that it's at t2 is equal to 10 seconds. So that doesn't help us really sort of sort things out. Gives us some information, but we have to think a little bit more about what's going on. Well, we're interested in where the center of this circle is here. And there is one thing that we know, no matter what the radius of the circle is, we know that the y position of that center is going to be 6 meters, because no matter what the radius of the circle is, it's got to be sort of oriented along this line. So we can conclude that this guy is got to be 6 centimeters, so we actually have 6 meters rather. We actually have half of the problem done. And then the question is, what's this guy here, the x position, the center? You can see you can make a little more progress even by recognizing if we know the radius of the circle, of the motion, then in fact we know that we're over a distance 5 meters at that point, and then we're over another distance r to get to the center. So we've kind of got things worked out. We just need to figure out the radius of this circle of the motion. So how are we going to use that information, or how are we going to use the information given in order to find that? So you can go back and think, all right, well, what equations do we know that use the radius of the circle? And the one that comes to mind initially, I think, is the centripetal acceleration is v squared over r. So can we use that in order to find the value of r? Well, we know the speed, but unfortunately they don't tell us what the acceleration is. So scratch your head a little bit and say that's not going to work. What else do we know that involves the radius r? And here, this is, so the other equation that we have is this fact that the speed is given by the distance divided by the time. 2 pi r, the circumference of the circle, divided by capital T, the symbol we usually use for the period, the amount of time it takes to go all the way around in a circle. So do we have the period? And now here's where this 4 seconds and 10 seconds comes into play. Because we know at 4 seconds we're here, and we know at 10 seconds we're there. And so, in fact, the particle's gone around the circle 3/4 of the way around when it gets to this point. And so we can write down that the difference in those two times is actually 3/4 of a period. And that gets at this last piece here that says T2 minus T1 is less than 1 period. So what was that about? Well, you see, it's possible that this thing, if it was here at t is equal to 4 seconds, that it went around once and again before it ended up here at 10 seconds. So it's possible that, that it's not just 3/4 of a circle, but the fact that it says T2 minus T1 is less than 1 period allows us to write this formula down in that fashion. So then it's actually relatively straightforward to solve that for T. Just move the 3/4 over as a 4/3. We know T2 and T1, so we can put those numbers in, and 4/3 times that gives us a total time of 8 seconds. So it's 8 seconds is the period, and now you can see we're in good shape because we can use our equation to figure out the radius. So let's slide that equation on down there, and then we'll solve it for the radius. So just move the t over and divide by 2 pi. And now we know those numbers. We know the speed, we know the period, and we know 2 pi. So you can put those numbers in, plug them into your calculator, and we end up with 3.8 meters. So that's now pretty much where we need to be. We know that the radius is 3.8 meters. Now notice, it looks like my smaller circle, let's go over and use the smaller circle then, is actually closer to the way this is actually working, right? Because 3.8 meters means that the radius doesn't get you down to the x-axis the way I had drawn the other picture. So now that we know the radius is 3.8 meters, we're in pretty good shape. Now we can just put that into this expression to say the x position now is the 5 meters over plus the radius 3.8, and that gives us our final answer that says the x position is 8.8 meters and the y position is at 6 meters. So sort of a challenging problem, a little bit different. Turns out we never even had to use the v squared over r, which is our sort of famous formula for the rotational motion. But we've worked out the answer just by plugging through sort of our conceptual understanding of what circular motion is all about.